Good morning. I will talk to you about some work we've done on simulating turbulence to see what happens to optical links in a two-way configuration between the ground and satellites. This was done in collaboration with ONERA, which is the French aerospace lab, and the CIRT from Observatoire de Paris. As you know, the best optical clocks these days reach 10 to the minus 18, and it's difficult to compare them. We know how to compare them in optical fibers, using two-way configurations in optical fibers. However, many applications will require using free space links, either over short distances, if you're going to walk a clock around, for example, for geodesy using clocks, or indeed, if you want to use clocks on satellites, well, fibers are not very practical. So there has been some work in the last 5 years or so on optical free space links through the turbulent atmosphere, and I think we will hear a very interesting talk on recent results on that just after mine. And well, the underlying question is, if you extend these links to long distances, in particular to space, are you limited by atmospheric turbulence? If yes, at what level is that limit? And is it a showstopper? The main problem is that if you're going to shoot up to a satellite, you will have a pointer-head angle. So when the satellite is moving, your uplink will go at an angle which is relatively large. Concerning turbulence, I will talk about that in a minute. Will go through a different atmosphere than your downlink. So that means you will have phase noise that is non-reciprocal between up and down, which means your two-way configuration will not cancel that noise. And does that mean that you cannot work on a two-way free space link to a satellite? We don't know, and we had good reasons to believe that in fact it would not work, or not as good as we hoped, and I will tell you what we found out. This has been published recently. The reference is down there, so you can look up all the details of what I will be saying. A bit of the background. So here's the type of link we're imagining. There's a clock up in space, one on the ground. There's a turbulent volume of air close to the ground telescope. There's a laser going up and a laser coming down. The red one in this case is going down, coming down, the blue one's up. It's just, they're the same frequencies, just to distinguish them. And the measurement is very simple. On board, which is on the top left-hand side, which you cannot see, but it's the similar thing as on the ground. The incoming laser, so on the ground sketch, it's the red laser, is combined with the local laser, the blue one, and you measure the beat note, and you measure its phase and its amplitude. And the local oscillator laser is also emitted towards space. And you see one reason you would have asymmetry between the two is on that little sketch. Your apertures for the emission and for the reception might be different. You might want to do that because you have lots of power on emission, so you want to spread your laser so your pointing is easier, and you want a big telescope for the few photons you would get on reception because your laser on board is weaker. You also have asymmetry as shown there due to the pointer head angle. And so you might have a number of reasons of asymmetry. If your two paths are perfectly symmetrical, and that's been shown by Shapiro in 1971, and then by the same Shapiro back in 2012, for different configurations, you have complete reciprocity. That means your two links are totally symmetric, and your phase noise in particular on the way up is the same as on the way down. However, when you have asymmetries, what residual phase noise do you get? And that's the question we're trying to answer. And we also want to characterize the signal-to-noise loss due to turbulence, which is, of course, one of the main problems. It's just that your signal will be flickering like the stars are flickering when you look at them through the atmosphere. So how do we characterize the phase noise and the signal-to-noise loss? So what we do is we will simulate propagation of the emitted electromagnetic fields through the turbulence, and I will tell you on the next slide how we do that. We generate time series of about 8-second durations with one point every millisecond. For each of those millisecond points, we have a complete map of the received field in the received aperture. So we have its complex amplitude and phase. And then we calculate two quantities which we will be interested in the following. One is the phase. which is the overlap integral, the argument of the overlap integral between the complex field of your local oscillator projected onto the receiving pupil and your signal that arrives. And the second quantity we're interested in is the heterodyne efficiency, denoted M, which is the same overlap integral. It's just its amplitude squared, and that gives you the signal-to-noise ratio on your heterodyne beat. And we normalize it to the same signal-to-noise ratio in the absence of turbulence. So if the beam propagated through vacuum. That means we have a sort of loss of signal to noise with respect to your optimum signal to noise that you would have if you were just short noise limited and you went through turbulence. And you went through vacuum, sorry. So how do we do that? We use a Fresnel propagator that propagates the electromagnetic field from the emitter through the atmosphere. The atmosphere is simulated by a number of phase screens that move on one hand due to wind, on the other hand due to the motion of the satellite. So the line of sight is actually moving through the atmosphere, and that's in fact the main effect. We consider a low Earth satellite, or rather a satellite in an elliptic orbit coming very close, which is the really worst case you can get. Satellite velocities of about 9 kilometers per second, which means you have a point-ahead angle, it's written just underneath, of about 63 microradians to be able to point to the satellite. The turbulence conditions we are considering are free radius of 13 centimeters and 5 centimeters. 13 centimeters would correspond to something you would have at an astronomical observation site, at an altitude site, on a decent observation night. 5 centimeters is worse. It's something, in urban areas it would be even worse than that, but that's something I would expect you would get, say, on a plane somewhere, I don't know, maybe where NIST is located, certainly not in the Paris area, way worse. We consider a satellite at 20 degrees elevation, at 3,200 kilometers at perigee, so it's passing through very fast at that distance from the observatory. On the satellite, we consider symmetric apertures, so the emitting and receiving apertures are the same. On the ground, we consider two cases where the two are the same, 40 centimeter each, and where the emitting aperture is smaller than the receiving one, only 15 centimeters. And we implement tip-tilt correction on the received field to remove the main orders of turbulence. The reason is that you need tip-tilt correction anyway if you want to track the satellite. So here's first results. Heterodyne efficiency. On the left-hand top corner, you see the downlink without any tip-tilt correction. So it's just the field, the overlap integral of the two fields, normalized to the same integral when you have no turbulence. You see, so when it's equal to 1 up top, you would have optimum signal to noise. So you see that the average, it's written underneath, it's about 0.18. So you lose about a factor 5 on average on your signal to noise, which you can live with. However, the problem is that you see there's these huge big extinctions, the dips going down. You can lose as much as 10 to the 6, so 6 orders of magnitude on your signal of noise over those 8 seconds that we looked at. And that means that you essentially have very frequent extinctions of your signal. If you use a 15 dB detection threshold, that means you will most of the time see nothing, or much of the time. It's the red line you have on there. So the problem is really these large fluctuations. You see that things get a lot better on the right-hand top panel, where we have the same data, but we use tip-tilt correction. We implement a correction for tip and tilt, and you see there's only one extinction left that goes below the 15 dB level. The average is, on average, you lose only half of your signal to noise, but the more important thing, in my view at least, is that you have very much smaller fluctuations around that average value. And now the other interesting thing we found out is what you see on the bottom right-hand panel. There you have the uplink with a pointer head angle. So what we do here is we assume we take the tip tilt correction that we measured on the downlink, so how the phase was tipped and tilted on the signal that came down, and apply it on a pre-compensation onto the uplink, which is sent up with a different angle by 63 microradians. Now you would think that that over that angle the turbulence is relatively decorrelated, so we would not expect an improvement on the uplink. In fact, you get a very large improvement, almost as good as on the downlink. You see the average is just slightly smaller and the fluctuations are just slightly larger. But in fact, you have almost the same. And that is related to the fact that the very low orders of turbulence, piston and tip tilt, they are correlated over much larger angular separations than what is typically known as the isoplanatic angle in standard astronomy and in adaptive optics for large telescopes. So indeed, if you're limited by the first orders, and this is the case here, then pre-compensating the uplink by the tip tilt you measured on the downlink, in fact, works very well, much better than I at least had expected. If you do the same for a stronger turbulence case, well, the results are conserved as you would expect from theory, as long as your telescope diameter to Fried radius ratio remains the same. So if you want this to work in 5 centimeter Fried radius turbulence, so in a more turbulent site, while your telescopes have to be smaller by about a factor 3, which means, of course, that you need more power to have a decent signal to noise. Some more results on the okay. So this is on the phase noise. So here on both slides, on both panels, you see the red line, which is the downlink, and the black dotted line, which is the uplink, which you can almost not see because the two are totally superposed. In fact, and this is after tip tilt correction again, and it turns out when you do a modal analysis of the fields you receive that the red as well as the black represent is about 99.9% of the red and the black are the piston. So the remaining lowest order turbulence, which is just phase motion like this, okay? So because you've removed tip tilt is coupled to higher orders, but they're small, so you're left with essentially just piston noise, which is fluctuations of phase along the line of sight. And they're the same for the uplink and downlink. So when you do the difference, you get the green lines on those graphs. So here I have plotted two cases which show you the effects of the two asymmetries, the two main asymmetries independently. So on the left-hand side, you have the same apertures on reception and emission on the ground. So your local oscillator sees the same field as in the one you emit into. And however, you have a pointer head angle, so the two are separated just by an angular separation of 63 microradians. And you see that you have some remaining noise, which looks a bit like short-term noise, but it's small. On the right-hand side, we have taken a sort of artificial case where you have no pointer head angle, so you're shooting up exactly the same way as it came down. However, you have different apertures on reception and emission, so your two fields sample different turbulence. You see, again, they're very similar. However, the residuals are roughly of the same order of magnitude, the green noise, but have a different structure. Again, when you go into stronger turbulence, you conserve exactly the same thing as long as you adapt your diameters. If we plot the same thing, if you look at the stability analysis of the graphs you have just seen, of the phase noise you have just seen, so the black line is just the stability of the red line here, okay? You see that you're in the 10 to the minus, so it's a modified Allen deviation. You can't read it, I can read it, but it's too large for that one. So it's modified Allen deviation. You see the back line, you're in the 10 to the minus 14 regime, and it goes down slowly, typical Kolmogorov turbulence type evolution of the noise. You will have a hard time reaching 10 to the minus 18 on any integration time with a one-way link, essentially. However, when you do the difference between uplink and downlink, which are the three other curves, you see that they go down very steeply. Now, first look at the short term on the left-hand side. The dark blue curve is the one that has no pointer head angle, so it corresponds to the green curve on the right here. So you see that the turbulence or the pointer head angle asymmetry in the turbulence plays a role on short integration times. The red one is the one that has identical apertures for the uplink and the downlink and the pointer head angle. And the light blue has different apertures and the pointer head angle. So you see that the difference in apertures, the fact that you're sampling different fields, will add noise on the long term, but not on the short term. So essentially, the message here is if you're looking for good long-term stability, you have to be careful in your design of your links to make sure that your local oscillator and your emission sample the same kind of turbulence. And that brings me to the conclusion. So the asymmetry in optical links, whether it comes from technical things like the apertures you'll be using, or from things that are unavoidable like pointer head angle, leads to non-reciprocity of turbulence noise, and thus residual noise in two-way compensation schemes. Of course, as we all know, it leads also to large losses of signal-to-noise loss. Now, the first thing we found out is that tip-tilt correction, of course, helps you for the signal-to-noise loss. That we knew from astronomy since many, many years. But, and that's the interesting thing, in spite of a large pointer head angle, much larger than the astronomical isoplanatic angle, you can apply the downlink tip tilt that you've measured on the downlink onto the uplink, and it works quite well. The second thing that we also found out is that the phase noise also remains highly reciprocal in spite of the pointer head angle and of asymmetry of the apertures. And that the two are related to the fact that in the end, once you have corrected for your tip tilt, you're left only with piston, mainly with piston phase noise. So, as I said, the asymmetry from the pointer head angle dominates at short term, the asymmetry from apertures at the long term. So a careful design is important if you want good long-term stability, which you want here. So for the situation we have considered, you can reach about 10 to the minus 17 modified Elm deviation in only 1 second averaging time. So that's really, really steep. We've used the standard profiles that are used for astronomical turbulence simulations in all observatories. So we're relatively confident on the models we've used. And that, of course, is highly promising for space applications, certainly not a showstopper. What we will do next, well, we'll look at different apertures. In this case, the two apertures we looked at were co-located. What you will do more realistically in a scenario, we'll have two separated telescopes, one for emission, one for reception, so that we have not looked at yet. Try and use actually measured turbulence profiles, which should be even more realistic than what we've used, and go for longer durations below 8 seconds, longer than 8 seconds, which is a question of, in fact, computer time or having a large enough computer. So I'll tell you about that next time. Thank you.